Okay, question 23. We have another momentum collision conceptual problem. So two different experiments involving a puck colliding with a block. The puck is initially moving here to the left. So the both experiments are on a flat frictionless surface. So we assume the net force on the system of the block and the puck are 0. They have the same mass m. The block has an unknown device that may activate during the collision, resulting in different outcomes to the experiments. Both experiments begin with the block initially at rest and the puck has an initial momentum to the left of magnitude p0. After the collision in experiment 1 the puck is at rest. Experiment 2 the puck has a final momentum to the right of magnitude p0. So the magnitude of the final momentum of the block in experiment 1 greater than, less than, or equal to that of the block in experiment 2. So in this question, it's a good challenging question. And sort of maybe explain somewhat qualitatively first. Initial momentum, since it's a flat horizontal frictionless surface, there are no net forces on the puck block system. So whatever momentum is in this system at the beginning must be in the momentum at the end. So the initial momentum of the system is just the mass of the puck times the velocity of the puck, which is just p0 to the left. So in experiment 1, since the puck is at rest, the block must have a momentum of p0 to the left, so that the initial momentum equals the final momentum. And in experiment 2, since momentum is a vector, if the puck is carrying a momentum of p0 to the right, and if we want to have a momentum of p0 to the left at all times, then the block here in experiment 2 has to have 2 p0 to the left. To cancel out 1 p0 to the right, leave you 1 p0 to the left, so the momentum of the block in experiment 1 is less than that in 2. But I'll go through a little more detailed analysis that's very similar to the tutorial analysis, where we can have draw a grid here. So we have the block, we have the puck, and we have the system. And then we do initial one, final one, and then do initial 2, final 2. Let's draw a rough grid here. Let's start here. What we know is that the initial momentum of the block is 0. The initial momentum of the puck is to the left, and now maybe I'll draw this. I'll do sort of 1.5 centimeters on my ruler. And this is p0. Or 1.5 units. You want to think of that as sort of putting it quantitatively. So initial momentum of the system is 1.5 units. P0 or 1.5. And the final momentum of the puck in experiment 1 is 0. There is no change in the momentum of the system since there's no net force. So again, we have to have 1.5 units. So if the momentum of the system is 1.5 and the puck has no momentum, the block has to carry 1.5 units of momentum. Again, this 1.5 is completely arbitrary, it's just a unit on my ruler. I wouldn't read into it too much. It's just p0. Why define as p0? So that's the experiment. So this is the momentum of the block in experiment 1, as I mentioned in the early part of the video. Now initially 2, though again the block is initially at rest. The puck again moves in, it's the same, so I guess I could just get the same diagram, but p0, so the momentum of the system is still 1.5. Now but here the puck moves with a momentum of 1.5 to the right. So it has a change in momentum. So again, 1.5 units. Now we want the momentum of the system to be 1.5 to the left. So if we have a 1.5 vector to the right and we want to end up with a net of 1.5 to the left, the momentum of the block must be 3 to the left. 3 units. So maybe I should label these as negative. This is negative, this is negative, negative, and this is plus. So if we have negative 3, this would be 2p0. There's certainly these are magnitudes that, in order for the momentum of the system again to remain always p0 to the left, if the momentum of the puck in experiment 2 is carrying p0 to the right, then the block must be carrying 2p0 to the left, such that we're left with 1p0 to the left. And that means that the momentum of block 2 is twice as big. The final momentum of block experiment 2 is twice as big as that as the momentum in experiment 1. So it's definitely less than. The correct answer is less than.